Hi everyone, welcome back. In this video we're going to basically finish off magnetic fields by looking at one of the practical uses for magnetic field. So from your study design, basically we've got this: investigate and analyze theoretically and practically the operation of simple DC motors, direct current motors, consisting of one coil containing a number of loops of wire which is free to rotate about an axis in a uniform magnetic field and including the use of a split ring commutator. Okay, so we're basically looking at how DC motors work. Simple DC motors, very, very simple motors. Okay. So, first of all, you don't really need to know about this too much. It's just more of a reminder of what's going on, because you might hear the word torque, and if you've never done units 1 and 2, you might not know what that is. So basically torque is the rotational equivalent of force. Okay, you normally apply a force to make something move in a straight line, but torque, if one end of the object is held into place, torque is basically a measure of the amount of force needed to rotate the object. Okay, so here's a very simple setup. You've got like a door and a hinge over here, and you want to open the door. Okay, now the door is free to rotate along this axis where the hinge is. You can choose to either push the door close to the hinge, or you can choose to push it further away from the hinge. Okay, and you can go and do this yourself if you're in your house right now. Just go and try and open a door from both points. All right, and you should find that it's easier to open the door if you push it from the end. Okay, so what's going on there is you are applying more torque to the door, which means it's going to be easier to open the door. Okay, and there's a very simple relationship between torque, how far you are from the pivot, and how much force you are applying at that point. Basically, the equation is this. Okay, torque is equal to the distance you are from the pivot multiplied by the force that you are applying at that point of contact. Okay, and you can see that this distance here is much shorter than this distance here, which means that the torque is going to be smaller if you apply your force here than it would be if you applied it over here. Okay, meaning that it's easier to open the door if you push it from further away from the hinge. That's all that's saying, okay? But basically the main idea is torque is the rotational equivalent of force. It's how easy it is to make something rotate, okay? All right, now that we've got that out of the way, let's talk about how a DC motor is constructed. So what I've got here in this picture is basically a loop of wire, and it has a current passing through it. Okay, so forget about how this would actually be set up in real life. I know you sort of need a bit of wire to come off the end to be connected to battery or some kind of source, but don't worry about that for now. Just pretend in magic physics land that this is a real thing. Let's think about the forces that are acting on the sides of the loop. Okay, so if you look at side AB, okay, use your slap rule. Okay, you can see the magnetic field lines are pointing to the right, so stick your hand in front of you, put your fingers to the right, your thumb will sort of be going into the page, as indicated by this side of the coil AB, and your palm will be facing downwards, meaning that that side of the loop is going to experience a downwards force. You can do the same thing for the other side, side CD. All you're really doing there is rotating your hand so your thumb points out of the page, and you should be able to see that your palm is pointing upwards, meaning that this side is going to be experiencing a force upwards. Now, if your loop happen to be sort of attached to this axis here, indicated by these dotted lines, what's going to happen is your loop is going to begin to rotate. Okay, this side is going to get forced downwards, this side is going to get forced upwards. You can imagine your loop is going to start rotating in an anti-clockwise direction, according to this diagram. All right. You can also analyze the forces on the other sides, BC and AD, but in this position, at least, there won't be any forces because your current is parallel to the field. Okay. But the main thing is, these two opposite sides are going to experience opposite forces, and if it's attached to sort of like a shaft or some kind of axis, then it will begin to rotate. Okay, so it's going to start rotating anti-clockwise. in sort of the next moment in this top diagram here, that's what you've got. Okay, so again, you can talk about the forces acting on side A, B, and C, D, use your slap rule, and you should still see that the forces are the same as what it was just a moment ago. Okay, the force on side AB is still going to be down. The force on side CD is still going to be up. So it's going to continue to rotate anti-clockwise. Now it's interesting to know that in this position, because these two sides, BC and AD, because they now have a component of the current that is perpendicular to the field, those two sides will also start experiencing a force. However, because those two sides are completely opposite each other, the forces are going to cancel each other out. There's no torque because they're not perpendicular to the axis of rotation, which means that those two forces aren't going to affect the rotation of your loop. Okay, so these two forces on AD and BC, you can ignore them. Know that they're there, just know that they're also not going to affect your rotation. Okay. Now, again, it's continuing to rotate anti-clockwise. Okay. So in the next diagram here, this is what would happen if it was to rotate 90 degrees from its starting position here. And again, you can use your slap rule and you can determine that the forces on side AB are still downwards, the forces on side CD are still upwards. So nothing has changed in terms of the direction of the forces. However, now in this position, the torques from each of these two sides are going to cancel out and it won't continue to rotate anymore. Okay, it's sort of going to be stuck in this position. All the forces cancel each other out. There's no more torque. It's just going to stay there. Okay. Now, in real life, what might happen is because it was initially rotating anti-clockwise, it might continue to rotate past this point due to its inertia. But again, you can analyze it with a slap rule and you'll see that this side will still have a force up, this side will still have a force down, and it's just going to swing back to this position. Okay, it might sort of wobble back and forth for a little bit, but eventually it'll sort of stay in this position here. Okay, now that's not very practical. We want our motor to continue rotating. We don't want it to stop when it gets to a particular position. And we've got a way to fix that, which I'll show you in a second. First of all, let's do a question. So we've got this single square coil of wire, side length 5 centimeters. It's free to rotate within a magnetic field B of strength 1 times 10 to the negative 4 Tesla. A current of 1 amp is flowing through the coil. What is the torque on the coil? Okay. Now, typically you won't get a question talking about torque in a Year 12 exam because it's technically not part of your Year 12 study design. The extent to which you get asked a question about this kind of thing is just to determine the forces on either side of your coil, okay, which should be pretty easy because basically all we've got is a length of wire with a current going through it in a magnetic field, okay, and we already know an equation for the force on that kind of situation. It's NBIL, okay. However, we don't want the force, we want the torque. Okay, but we've got a very simple equation for the torque. It's equal to R times F. R is the distance from the axis of rotation that you are applying the force, which is basically, in this case, that length here. Okay, which if the coil is 5 centimeters square, then this length here is 2.5 centimeters or 0.025 meters. Okay. So that's some important information to know. However, notice that to work out the torque, we need to know the force first of all, so we've got to work this out anyway. All right, so let's just work out the force on one side, and then we can multiply that by 2, and then multiply that by the distance, and then that'll give us the overall torque. So if this is just a single loop, okay, it doesn't have multiple coils going around, it's just a single loop of wire, that means N is 1. B is the magnetic field strength, so 1 times 10 to the negative 4. I is the current, which is 1 amp. And L is the length of the wire that is inside that magnetic field. So we're talking about these sides AB and CD. So let's just talk about side CD. All right, it's a 5 centimeter square. That means this length is going to be 0.05 meters. Okay. And what you end up with here is something along the lines of 5 times 10 to the negative 6 newtons. Okay, so this side experiences a force of 5 times 10 to the negative 6. This side AB also experiences the same force, just in the opposite direction. Okay, and because the two forces are sort of offset from each other and they are a certain distance from a pivot point, that means there will be a torque. Okay, so what is the torque on just one side? So let's talk about side CD. The torque on side CD is, well, how far away from the pivot are we applying the force? It's 0.025 meters multiplied by the actual force, which is 5 times 10 to the negative 6. And we end up with 1.25 times 10 to the negative 7 Newton meters. Torque is Newton meters. However, we've also got the other side AB to worry about. Okay, we've just worked out the torque on CD. If you want the total torque on the coil, you've got to multiply this torque here by 2, because there's two sides that are applying opposite torques, making it rotate. So multiply that by 2, you get 2.5 times 10 to the negative 7 Newton meters. Okay, so just again, you're not really going to be asked a question about torque in a Year 12 exam, at least not a quantitative question with numbers. The extent to which you'll get asked a question, hopefully, is just working out the force on a particular side of the coil that happens to be in this magnetic field. Okay, so there we go. All right, so let's just recap again what's going to happen with our coil. So here we've got a coil, and this is more practical. We've got a way for the current to actually get into the coil in this case. So you can see that there's something happening outside of the view of the picture. The wire comes in on the left, the current's going around this way, then down from CD and then out that way. Okay, so that's a bit more practical. So again, using your slap rule, just remember, field lines go from north to south, so the field is going to the right in each of these diagrams. Use your slap rule. Figure out which way the forces are going to be pointing on each side of your coil. Okay, again, using your slap rule, you should see that the force on AB is down, the force on CD is up, which means that the coil is going to begin to rotating anti-clockwise. Okay, so that's position 1 here. The coil begins to rotate anti-clockwise. Position 2. Again, using your slap rule, you can still see that the force on AB is down and the force on CD is up. Don't worry too much about that the coil is going outside the region of the magnetic field. This is just in sort of like a simplified diagram of what's going on. But your coil will still begin to rotate. Okay, it's still rotating in an anti-clockwise direction. Now, in position 3, okay, this is what we were talking about before. Once it reaches this point, there's no more torque. Okay, so the forces on AB and CD, they don't contribute to the rotation anymore. However, because it's got inertia, because it might have some momentum, it might continue to swing past this position, rotate past this position into position 4A. However, again, using a slap rule in position 4A, you should still see that the forces on AB and CD are going to make it so that the loop just rotates back to position 3. And like we said before, it might just sort of wobble back and forth, but eventually it would come to rest in position 3. Okay. Now, in order to avoid this happening, what would be really good is if we could, once it swings past this position 3 into position 4A, it'd be really good if we could maybe like switch the current, reverse the current, make it point the other way so that your forces point in the opposite direction, allowing it to continue rotating. Okay, so one way we could do that is to reverse the current. Another way we could do it is to reverse the magnetic field, but that's a little bit impractical. There is a way to reverse the current, okay? And the way that we do it is we use this thing called a commutator, okay? Or you might hear it be called a split ring commutator. Basically what's going on is you've got, some sort of battery, some sort of voltage source connected to what we call brushes. Typically they're made out of carbon or some kind of similar material. And they're conductive. And what happens is the current flows from the battery through the brushes to this thing called a commutator. And the commutator is split into pieces. And each piece is connected to a side of the coil. So you can see this piece here on the left is connected to this part of the coil. And what's going to happen is your current's going to go that way, through this brush, through this piece of the commutator, go around the coil, go back down this way, through this piece of the commutator, back through this brush, and complete the circuit. What's important to know though is that this commutator is not connected. Okay, so what I mean by that is that the pieces of the commutator are not touching each other. All right, so notice what happens here. The brushes aren't actually sort of like stuck to the commutator. They're just brushing up against it. That's why they're called brushes. So what's allowed to happen here is that this coil, including this commutator, is allowed to rotate, while the brushes and the rest of the circuit containing the battery remain stationary. Okay, and you can see that once this commutator rotates another 180 degrees, this piece of the commutator is then going to be attached to this brush, which is connected to the positive terminal of the battery. Okay, and what's going to happen is instead of the current going down this way out of this commutator piece, it's going to now be going into that commutator piece and going around the circuit again. Okay, so the function of a commutator is to reverse the current every 180 degrees of rotation of the coil. Okay, and in doing so, it allows the forces to switch their directions, so that what was initially sort of this force on this side, if we were to give the coil some names, A, B, C, D, the force on this part of the coil AB is initially upwards. Once the current reverses its direction, the force would be pointing downwards. Okay, and when that happens, notice in this position, the coil is going to begin to rotate anti-clockwise. So eventually this side AB is going to be in the position where DC is at the moment. So in 180 degrees, these names would sort of flip around. And what you want to happen is you want now the current on AB to be moving in such a way so that the force on AB is now down instead of up as it was before. So you can continue rotating the coil around in this anti-clockwise direction. Okay. Now it's a little bit tricky for me to explain this over a PowerPoint with just my voice and some poorly drawn diagrams. So what I'm going to show you, which will hopefully explain things a little bit easier, is a bit of a simulation. Now you can go to this website yourself. I'll switch to it now, so just give me a second. Okay, so this is let me explain what's going on here. This thing here is basically your magnet. Okay, if I turn on the magnetic field lines, you can see that this red part would be the north pole of the magnet, the green part would be the south pole. But I'm going to turn the field lines off because it's going to get confusing. So just remember the field points downwards. Okay, now here we've got a coil connected to a battery or some kind of DC voltage source. And this picture is actually rotated 90 degrees from the diagrams in the PowerPoint. So if I go here, imagine the whole thing being rotated 90 degrees to the right. Okay, so just be aware of that. Okay, so let me just reset this. Okay, so what we've got going on here is we've got the battery here, positive terminal, current's going to go out of positive through this brush here into this commutator. This commutator is attached to this side of the coil. And so what's going to happen is the current's going to go around this way, down that side, down along this way, back out of this commutator through this brush into the other side of the battery. Okay. Now, if you use your slap rule, just remember the field lines are downwards. You should be able to use your slap rule to figure out that the force on this top side is going to be to the left. Okay. And because this current is always going to be perfectly perpendicular to the field lines coming out of these magnets, it will always be pointing to the left. Okay. Now, what I'm going to do is start this animation, and you'll notice that the coil will begin to rotate. I'm going to pause it just before the current flips over. Okay. So, right at this point, you you can see that this side of the coil, which is attached to this piece of the commutator, is still just touching this brush. So the current is still going what I might call into the page, and the force is still pointing to the left, okay? And notice the forces are still pulling this coil around. However, if I was to just keep going, now this is a highly exaggerated commutator, this doesn't really happen in real life. At this point, the commutator is not touching the brushes at all. So what's going on in this idealized motor is that there are no forces acting on any of the sides because there's basically no current going through the coil. And so the coil is continuing to rotate under its own momentum. Okay, it's continuing to rotate, so this side is going down and this side here is going up. Now, you got to remember, the current on this side here a moment ago was into the page, okay, because it was connected via this commutator to this brush. But what's going to happen is as it continues to rotate, this commutator now, which was connected to this side, is going to become connected to the negative terminal. And the other commutator will be connected to the positive terminal. So basically the current on each of these two sides is going to swap its direction. So this current, which was going into the page, should now be out of the page. And same with this side here, the current was going out of the page this way, but now it's going to be going into the page like that. Okay, so let's resume. There we go. Okay, so now this part of the coil is connected to the positive terminal, whereas before it was connected to negative, which means that the current in this coil has now swapped direction. Okay, and again, you can use your slap rule to determine that this side of the coil will be experiencing a force to the left, the other side down here will be experiencing a force to the right, and so the torque on the coil will make it so that it continues to rotate in this anti-clockwise direction. Right, I'm going to let it run for a few seconds just so you can see what's going on. Okay, pulled around, current flips, and the forces on each side change. Okay, and you'll notice that the forces, they keep changing so that there's always this continuous torque, allowing the coil to just continue rotating indefinitely. Okay, so you can have a play around with that. Website's up here. Okay, Walter Fendt. There's so many good animations that he's got on his website. It's amazing. I highly suggest you check it out. Anyway, back to the PowerPoint. So that's basically the function of a DC motor. Okay, you've basically just got a current in a magnetic field going through a wire. That wire is going to experience a force. So you've got two wires experiencing forces in opposite directions. They're allowed to rotate, and that's your motor. Okay, and in order for your motor to continue rotating, you need to have this thing in your circuit called a commutator, which basically reverses the current every 180 degrees so that the forces on each side of the coil swap, allowing it to continue rotating. That's it. Okay. Now, notice that if for whatever reason you turn off your motor and it stops in this position, you're a bit stuffed, okay? Because if you stop in this position and try and start the motor again, notice that this force on side CD will be up, this force on side AB will be down. It doesn't have any prior momentum, so it won't continue rotating. It'll just sort of stay in that direction, okay? How do you fix this? How do you fix a problem like this? You could jiggle the motor around a little bit, hoping to sort of get it out of this position and continue rotating again, but that's annoying. You don't want that to happen. So in most practical DC motors, you have multiple coils of wire going around your motor, okay? And your motor will always end up in such a position that there'll always be at least one coil of wire with a current going through it that is not in a position like this, okay? So no matter what position you stop your motor in, it'll always be able to start up again because there's always going to be some component of the force that is going to make it continue rotating, okay? So this is what a small practical DC motor would look like if you were to open up like a hobby electronics kit and you get one of those tiny little DC motors. You open it up, it'll look something like this, okay? So these things here, these metal things, these are your magnets. The magnets are stationary, they don't rotate. What rotates are the coils inside here, okay? And this thing here, this is your commutator. So this thing would be attached to your brushes, which would get the current from the rest of the circuit. And I think you can see this is actually a worn out commutator. You can see something going on here, which I think is the point of contact with the commutator and the brushes. You can see it's a bit worn out. And so that's it. That's a practical motor. Okay. So there you go. We've talked about motors. This is a practical thing that we can do with magnetic fields. And there you go. That's the end of the video and the end of this particular area of study, this particular topic. So we'll stop the video there and I'll see you next time.